Now that you've seen how sound works and how like humans typically hear, we're going to look at how we've created that in computers. So one thing to note, just kind of as we're talking about it, a human has an ear, but we would typically say a computer. The ear on a computer is just a microphone. Now the cool thing here is you actually know exactly what's happening here because you've looked at Faraday's law. So what we have for a microphone is you'll have a big flat surface or a tiny flat surface as we get smaller and smaller microphones. This is what we call a diaphragm. Diaphragm, I think that's looking right. But you can look up the spelling for it. You've got the diaphragm, which is also what we use for speaking, like if you've heard of your diaphragm in your chest. And it's on a speaker as well, because what we'll learn eventually is, and I'll kind of plant this seed now, the only difference between a microphone and a speaker is which direction it's running. So a speaker could be converted and could be turned into a microphone just by basically flipping how it's connected in. And a microphone could work as a speaker if you just kind of flip how it's connected in. Now, because we're optimizing for different things, they'd be really bad serving the other role, but functionally they do exactly the same thing. So now this diaphragm is going to get hit by the high and low pressure zones that we've talked about in the air. And that's going to cause this diaphragm to vibrate back and forth. Now the diaphragm will typically be connected, depending on the exact speaker design, but we'll say this one, it's going to be connected to a magnet. So I'm just going to essentially glue a magnet to the back of this large flat sheet. So that means when I'm vibrating this diaphragm, I'm also vibrating this magnet back and forth. Then what I do is I take a coil of wire and I just put that around the magnet so that when that magnet vibrates back and forth, it's moving in and out of a coil of wire. And what does that do with, we saw before, that creates a current. And the cool thing here is audio currents that we store will match perfectly to the vibrations you get in the air. And so this is what, if you kind of are into sound, this is going to be analog audio, because it's going to match perfectly. If you have a slightly stronger vibration, so a slightly higher amplitude, then this magnet moves slightly more, and it creates a stronger signal. Because as you probably saw in the lab or the exploration, if you move the magnet faster, you get a more powerful current. So in other words, if we have a louder sound hitting this, it creates a higher current, a stronger signal. If it's weaker, it doesn't vibrate as much, it doesn't create as much of a signal. Likewise, the frequency, the back and forth, perfectly will be paralleled here, because we saw that every time you move the magnet, that creates and changes the signal. So in other words, we can perfectly encode sound into an electrical signal. Now that electrical signal, unless that's going straight into a speaker, we have to store it somehow. But for now, I want you to kind of just get the idea that we're vibrating a diaphragm. It's going to create a signal in a wire, and that those two things perfectly match. The sound waves in the air can be perfectly replicated if you have a fine enough, detailed enough, precise enough system. It can create a perfect electrical replication. And what I mean by that is, if we imagine our sound wave as looking like something fancy like this, we can create this exact same shape electrically. in terms of like voltages and currents and stuff like that. So the sound wave can be perfectly replicated in kind of electricity, as it were.